So yes, I'm going to be talking today about using grazing incidence X-rays to understand solar cell materials. The first part of my talk is going to focus on how to understand a GIWAXS pattern just by looking at it. So this is a really common technique, and there's a lot that you can just eyeball with it, which is part of why it's so powerful. And then I'll talk about what GIWAXS can tell us about solar cell materials. I'll particularly focus on 2D perovskites because this was a central topic in my PhD. But I'll also give some examples related to polymers. So as I'm sure everybody has heard, halide perovskites make really efficient solar cells. And for those of you who may be more on the polymer side, the basic structure of a perovskite is shown on the left. So we have a metal in the center of these octahedra. We have a halide on the corners, and then a small cation, often an organic cation that sits in what's called the A site between the octahedra. So this is what is commonly called a 3D perovskite. And it's called 3D because this network of octahedra extends in X, Y, and Z directions infinitely until it reaches, for example, a grain boundary or a substrate. And perovskites are not only interesting for solar cells, they're also interesting for light emission. And this is because you can get every emission color in the visible spectrum from halide perovskites just by changing their structure. You can have the Ruddleston offer 2D perovskites with narrow emission. So Simon talked a few weeks ago about 2D perovskites. You can vary the number n of these octahedral layers that sit in these 2D slabs. So this would be n1, n2, n3, and so on. And these slabs are separated by bulky organic cations. Then you can change the nature of these cations. Now, these phases are interesting because if you change the number n, you can get emission that is tuned across the visible spectrum. And if you start playing with the bond lengths and bond angles of the octahedra, you really distort them. And this is correlated with broad emission, even sometimes white emission, which is interesting for white light LEDs. Now, in terms of solar cells, 2D perovskites are interesting because there are a lot of reports that they can boost the efficiency of the solar cell. You can combine a 2D perovskite with a 3D perovskite in the absorber layer of the device. And if the 2D perovskite is at the interface with the whole transport layer, this can suppress unwanted charge carrier recombination, which is interesting then because it boosts the performance. So for organic photovoltaics and halide perovskites, devices usually employ thin films. And so this motivates us to make sure we understand the structure of these thin films really well. In a typical lab X-ray diffraction experiment, which is how materials are often characterized in the lab scale, we have the X-rays, right, that come out that scatter off various planes, right, according to Bragg's law, which I think probably most people are familiar with. And in this diffraction mode, you get a lot of information, but only about planes that are parallel to the substrate, which is perfectly fine if you have an isotropic sample like a powder, which is usually the case for battery materials. But if you have an oriented sample like a thin film, you're missing a lot of information. So this is the power of GIWAXS, which stands for Grazing Incidence Wide Angle X-ray Scattering. You have X-ray beam coming in at grazing incidence. So this is usually not more than half a degree, but sometimes up to 2 degrees. And it scatters off of planes that are parallel to the substrate, as you can see here. So this is called out of plane scattering, or QZ. And you also get scattering from planes that are perpendicular to the substrate. So this is called in-plane scattering, or QXY. Now, these Qs here that I'm talking about are the GIWAXS equivalent of 2 theta. So you can convert 2 theta from your lab X-ray experiment to Q. And here, obviously, we have a different geometry, right? We're not measuring actually 2 theta. But if you're wondering what Q is, that's what it means. So this is really powerful, as I was saying, because we can probe almost all of reciprocal space. But notice that I keep cautiously saying almost all, not all. Why is this? So we have the X-ray that comes in at incidence angle, right, scatters off, and in the process, we get this scattering vector Q that I talked about, which is just the X-ray wave vector out minus the X-ray wave vector in. Now, Q actually forms a sphere, right, 3D, traced out by the radius Q, and we can look at the sphere with respect to our reciprocal lattice. So the reciprocal lattice, these points that you see here are equivalent to planes in real space. So, this point might be, the 110, or this might be the 202 or something like this. And you see that the sphere traced out by Q can intersect with these points, which correspond to planes. Now, when that happens, this is when you get scattering in your GIWAXS pattern. We can look at this coordinate system here, x, y, z, and the xy plane traces out this grid, right, which we see here. Now, Q and the reciprocal lattice do intersect in xy, so we get scattering in xy. But now if we look at the z-axis, you see that the sphere traced out by Q is going away from it. So we don't actually probe the z-axis, we probe maybe, here. So we're probing near QZ, and we're probing QXY or Q radial. So when you take a GIWAXS pattern, so this is poly-3-hexylthiophene or P3HD, which is commonly used in organic photovoltaics, your raw data will look something like this. You may use a nice color scheme like this one to get a pretty pattern, but you will have axes that are in pixels. You will have something cut off by the beam stop, so this blocks the direct beam from saturating the detector. And what you need to do to process the data is convert the pixels to Q, X, Y, and QZ, and also insert the missing wedge. So this distorts the raw pattern that you obtained to account, but not to worry. The lab X-ray diffraction experiment probes only planes that are parallel to the substrate. So if you want to get the complete picture of reciprocal space of your film on a bulk scale, you take the GIWAXS pattern and combine it with lab XID. So this is very powerful, especially for Halide Perovskites, where you can pretty easily use both techniques. So we can learn a lot of things about our crystallites in the film. This is again a poly-3-hexylthiophene. We can learn how they stack, their orientation. So for example, right, if we have the D100 spacing, and then over here we have the stacking 010, you see that both of these appear in the GIWAXS. Now, if the polymer is oriented a different way, you see that these peaks once again appear. They're just now in opposite locations. So the 100, which was in QXY, now is located in QZ because of the different orientation. We also learn how uniform the orientation is. So if we have isotropic orientation, no preference, we get a ring in GIWAXS. If we have some preferred orientation but with disorder, we get this sort of smear. And if we have a very highly oriented sample, we have a nice sharp dot. So now what is GIWAXS versus GSEPs? So grazing incidence wide angle X-ray scattering has a closer sample to detector distance, which allows us to probe large angles. So large in reciprocal space translates to small in real space. And so small being small angstrom, right, to small nanometer, which gives us information about things like inorganic lattices, polymer stacking, crystallite size, and also strain. If now we move the detector back, we probe grazing incidence, small angle X-ray scattering, because quite literally, we're just probing these smaller angles, but we're zooming in. So small angle translates to larger feature in real space. So here we're probing the larger nanometers to small micron regime. And this can give us information about phase separation between different polymers, block copolymers, bottle brush, how different bottle brush polymers can stack for those of you who may work on that. So what can GIWAXS tell us about Halide Perovskites? As I was saying, I did work during my PhD on these 2D Halide Perovskites with different N number. So the format that's used in devices most often, at least, is thin films. However, to explore new phases, what's most commonly done is to put the precursors in acid and precipitate out the perovskite phase. So you get these nice freestanding crystals that you can learn fundamental properties about. However, some of these properties don't match what people see in thin films for what supposedly should be the same phase. So if we look at the photoluminescence data here on the right, for the bulk crystals, or powder if you prefer, when we increase the N number, we see this nice shift to lower energy of the exciton emission. However, you see that this is not retained in the thin films. If for anything over n equals 3, the emission is practically that of the 3D perovskite, which you see here in gray. So why is this? The short answer is that there can be impurities, so inclusions of higher n or 3D phases, and the charge carriers funnel from these larger bandgap phases to the smaller bandgap phase, and so you get this bright red luminescence when maybe you were expecting something yellow or green. So this can be a really good thing. There's some engineering work that's been done in the field in high-profile journals showing that you can use this carrier funneling to get a really bright emission, much brighter than you would get from just having the 3D phase. However, if we are trying to study how a particular 2D phase behaves in the film, or if we want to make a device from a specific 2D phase, then we do need to control the phase distribution a little bit better. So how do we know that we have a particular phase? We look for the signature peaks. So these in the 2D perovskites are the OKO peaks. And what these correspond to are the stacking of a particular N on top of a layer of another N. So here we have a tri-layer slab on top of another tri-layer slab on top of another tri-layer slab. That will give us an OKO peak that corresponds to this particular stacking of slabs. OKO peaks are usually found below Q equals 1. So you just look at this region in the pattern and you can eyeball, oh, I have my phase, or oh, no, I don't. So which OKO peaks do we look for? The number and location of OKO peaks will vary with the N number. And usually for 2D perovskites, there's no other peaks in this region. So this is really useful to just say, oh, quickly, oh, yes, I have this, or no, I don't. I will point out that there are a lot of peaks that these phases share, and some of them are shared with 3D phases as well. So if you see a peak that that could be a 2D phase, it's good to check that it's not shared with other 2D phases or 3D phases. So how can GIWAXS tell us that we have a phase mixture? This was a simulation that my lab mate did of this butylammonium methylammonium metiodide phase. And when he made this as a film, he saw that actually the OKO peaks are completely missing. And he took a line cut, all right, and saw that in experiment, aside from some leakage from the beam stop, right, which gives this intensity, there's no OKO peaks, but in the simulation, we should definitely see them. This is because we have a phase mixture, so the long range order is lost. So here we have long range order of this tri-layer that repeats, but here we have a 4-layer, we have whatever type of layer this is, we have 2-layer, a 3D phase, and a single layer. So there are peaks that are common to all of these phases, which you see here quite strongly in experiment, but no peak from a specific layering. Interestingly, you can get peaks from the signature phases, but you can still have a phase mixture. So this was a study by the McNeil group of stacking fault defects, which, as the name suggests, is when the perovskite does not stack like it's supposed to. So you see the spacer cations here have the zigzag. Here you have 4 layers, 4 octahedra. Here you have 3. And this is not good, right? What they wanted was an N4 phase. So they obviously have a phase mixture, but they still saw OKO peaks corresponding to N3. And you can see here in the cartoon that they have a good long-range order of the N3 phase. When you have a high density of these stacking fault defects, that's when you get something completely intergrown like this, where all the different phases are combined into one. And from some TEM that I did, you can see in the nanoscale, in fact, that all these phases are mixed onto each other. So how can we make sure that the film is phase pure? We can get good bulk information from GIWAXS. And my favorite technique to combine this with is photoluminescence emission, because the carriers were funneled to these very emissive phases, and you can immediately tell based on the location of the PL peak whether you have this kind of impurity inclusion or not. If you're looking to see if you have higher gap phases than you wanted, you can also use absorbance. So the quickest, I think, is GIWAXS to look for the OKO, and PL to check that it's not redshifted. So why do we get this mixture of phases? We have competing solvation effects, right? We have alkyl chains of different lengths, we have a polar solvent, and we have inorganic salts. So it's really not so surprising that we have different phases that can form from this. But if we look at the fundamental property of the phase itself, we can zoom in right in this black box on the ions that make up the 2D sheet. We calculate the tolerance factor, which is a ratio of the different radii of these ions. And the tolerance factor will just tell us, based on its magnitude, should we expect a 2D phase, a 3D phase, not a perovskite. So we calculate the tolerance factor for the ions in this box. It's 1, and so that's the range in which 3D phases can form. So it's expected then that we would see these as impurities in films of this composition. So what we tried to do is we thought, okay, what if we increase this tolerance factor such that it's outside of the range in which 3D phases can form? And to do so, we went looking and we found this ethyl ammonium cation, which is large, and you combine it with bromine and you get a good tolerance factor for this purpose. So we further went looking in the literature and saw that the Kanatidis group a few years ago had published this very interesting structure where the A site and the spacer site are both ethyl ammonium, which is good because, the tolerance factor, but also the A site and the spacer are the same, so we avoid competing precipitations that could further complicate growth. And using this, we did obtain phase pure films. So now that I've told you this, I should probably try to convince you of it. This was the GIWAXS pattern of our ethyl ammonium lead bromide. We see nice OKO peaks in QZ, and we also see OKO peaks in QXY. We don't see any additional peaks. There's no peaks that are missing. So we confirm that we have this N3 phase in bulk. We also see that we have two crystallite orientations. So the fact that we have OKO in QZ tells us we have crystallite sitting upright. And the fact that we have OKO on their NQXY tells us we have crystallite sitting on their side. Now, if we take line cuts near in plane and near out of plane, then we can calculate the strain that these crystallites experience. And we find that the crystallites that sit upright have strain compressive along their long axis. The crystallites that sit on their side are compressed along their thinner axis. So now we want to test, do we have any small inclusions of 3D phases that dominate the emission? And the answer is no. So here is the photoluminescence emission of bulk crystals of the ethyl ammonium lead bromide in the light blue and films in the dark blue. So for both of these, we see the free exciton, which is the luminescence signature of this N3 phase. And then we see two features that appear at lower energy. One is this broad tail. The other one is this sharper feature. These arise from coupling of the free exciton to various phonons. So we see that we have this phase, but notice that there's less of this tail in the thin film. So why is that? Now I will explain the color scheme that I've been using for this perovskite. The outer octahedra of the trilayer are really distorted. The bond length changes hugely, right, from 2.75 angstroms to 3.31 angstroms. And when you have this type of octahedral distortion, that's what's correlated with the broad emission. There's a number of studies that show that when you apply strain to various lead bromides, if the strain that you're applying is increasing with these distortions, you increase the intensity of broad emission. But if the strain that you're applying decreases these distortions, you therefore decrease the broad emission. We know that we have strain in the film, we've measured it, and we see that we have decreased broad emission. So we think that the strain is probably why the broad emission is decreasing. So we have this ideal test case material, right? We can learn how the N3 phase would behave when it's cast as a film because of this sort of the chemistry, right? That we have this small cation that prevents larger 3D phases from forming, and we don't have these competing solvation effects. So how far can we deviate from this structure and still retain an N3 phase in films? So we started playing around with the cations, and one that was particularly interesting was formamidinium. So this is slightly smaller than ethyl ammonium, and it has different chemistry. Instead of having 2 carbons and a nitrogen, here we have 1 carbon and 2 nitrogens. So we just substituted stoichiometrically in the precursor solution, made our film standard way. And we saw that when we had small changes to the composition, this resulted in really big improvements to the growth. This is a simulation of the ethylammonium light bromide 2D phase, assuming all crystallites are oriented upward. So you see the OKO peaks and the 111. This is the pattern for the ethylammonium lead bromide film that I showed. Notice the disorder. And this is the GIWAXS pattern for the film with formamidinium substitution. Notice how closely it matches with the GIWAXS pattern of the simulated ethylammonium lead bromide, assuming all crystallites are upright. We have really defined OKO peaks. We have really defined 111. These are really small and sharp spots and not rings. So we have very uniform orientation of N3 crystallites of some phase that's very similar. I mean, obviously we're adding different things, right? This is not ethylammonium lead bromide anymore, but it's very similar lattice and is oriented uniformly like this. And we see correspondingly, the morphology of the film is much improved. We have micron-sized domains for the film with formamidinium, and we have lots of pinholes and very small domains for the ethylammonium-only composition. So we did a lot of structural characterization to try to understand, I mean, we're not adding very much formamidinium here. Why do we see such a big improvement? And we found actually residual solvent DMF that is contained in these thin films when formamidinium is there. There is literature on other perovskite compounds that reports that the extra nitrogen group of formamidinium can have this kind of hydrogen bonding with the carbonyl. And we think that this could be helping the growth in various ways. For example, formamidinium and DMF could be complexing in the precursor solution to make these really large seeds. And the formation of large seeds in the field is known to correlate with the formation of very large domains. Why are they all oriented like this? Well, if you have a large, extending layer, right, of this 2D sheet, it's more favorable for it to sit parallel to the substrate than for it to sit like this. Also, DMF doesn't need to leave the phase for an N3 perovskite to form. So it doesn't need to, therefore interrupt the stacking to leave. So we then checked the photoluminescence. Encouragingly, we do not see any large peak at lower energy that would signify a 3D phase, which you can form with high enough formamidinium. And we saw that at very high formamidinium substitutions, we got 3D phases, but for this level, not at all. However, we see, okay, the free exciton is still there. That's great because that's the optical signature of the N3. But this sharp feature that arises due to coupling with phonons, now with formamidinium has completely gone, right? We just have a little bit of tail here. So why is this? There is literature and studies showing that the phonon-coupled features can be very sensitive to how these cations pack in between the 2D sheets. And if we're starting to stuff solvent in the interlayer, this is not a very big interlayer, right? And then we're also hydrogen bonding. This definitely could disrupt the phonon modes that we think are coupling with that lower energy feature. So this is really interesting for trying to control the emission color for, say, light-emitting devices. But how is this relevant to PV? We see that the film has improved morphology, but does that translate to something that could be useful for photovoltaic? And in particular, the parameter that we want to look at is the absorbance onset. So for an absorbing technology, right, we want this to be a sharp absorbance onset with low electronic disorder. We see that our ethylammonium lead bromide film has crystallites oriented in two different ways. We also see that there are two, this is the absorbance onset of the free exciton specifically, not of various defects. We see that there are two absorbance onsets that are offset roughly what we would expect shifting of the free exciton. So yeah, this is not ideal. Ideally, we want we look at the ERBOC, the measure of the electronic disorder, is definitely higher than we would want, right? 54 MeV or 45. And this is not so surprising when we look at the SEM, right? We see all these pinholes, small domains, lots of interfaces where there could be unwanted carrier recombination or strain-induced source. For formalinium substituted film, encouragingly, we see only one onset. This is almost certainly because we only have one crystallite orientation. And if we calculate the Urbach energy, our measure of electronic disorder, we see that it's considerably lower, right? 37 milli eV. In contrast, right, is lower than 45 or 54. And this almost certainly is because we have these much larger domains, right? Fewer interfaces, pinholes that could contribute to electronic disorder. So, I'm early. So today I talked about GIWAXS, this very powerful technique where the X-rays per minute grazing incidence and give you these 2D patterns that probe most of reciprocal space. I discussed what these axes mean and why there's this missing wedge. You get a lot of information from this, like the phase, the crystallite orientation, how disordered is this orientation, and then also information about the long-range crystallographic order. You know, do you have stacking of the same 2D slabs on top of each other, or do you have this kind of intergrown phase mixture? I then discussed the test case of ethylmonium lead bromide, which is a really useful phase to probe when you're trying to understand how 2D perovskites behave as films, because this phase can be cast without any particular precaution as a phase pure film. I then showed how we can change the chemistry to obtain these really uniform sheet stacking, which fortunately yields lower electronic disorder, which is good for photovoltaics. So I wanted to thank the Chavinet group at UC Santa Barbara. Lots of people helped out with this study. For those of you who may be curious about the photothermal deflection spectroscopy, the really sensitive absorbance technique, this was done in Alberto Saleo's group. They're very open to collaborations if any of you want to send samples to them. I want to thank the funding sources and NGSE for the invitation. Here are the references of the papers that I described, except the one that's submitted, obviously doesn't have a DOI yet. And please do reach out on Twitter or by email if you want to further discuss. And thank you for your attention.